everyone, it's Wednesday, which means it's time for a new Chem Help ASAP live stream. Let me make sure. Okay, it looks like my mic is working. I'm going to wait for OG Benchmarks to let me know that the audio is coming through okay. Okay, so we've kind of been doing a series that is stoichiometry, but now we're going to really get into the nitty gritty of stoichiometry. So last time we talked about mole ratios and we did some mole to mole stoichiometry. And this time we're going to talk about gram to gram stoichiometry, but we're also going to deal with problems where you have like a density. So maybe you have a volume. And we're also going to do a problem where we've got gases. So we're going to use ideal gas law. So if you've got any questions, of course, just pop them in the chat. Okay, good. Audio's good. Okay, great. It's always nice to know that audio is okay. But yes, if you have any questions, just put them up in the chat, and I will do my best to explain them to you. Okay, so let's go ahead and get started. Problem number one. Why not, right? Okay, so we've got a balanced chemical equation. This is actually a solubility equation, if you will. So you can see we have most of these salts are aqueous, and then we formed a precipitate. That's just kind of an aside and FYI. All right, so our questions are A, how many grams of lead chloride are formed when 15 grams of aluminum chloride react completely? Okay, so this is very much a lab thing. You want to know how many grams of your solid you're going to form if you know how many grams of a reactant you've put in. This is a stoichiometry problem because we're given information about one molecule. We're asked information about a different molecule, but those two molecules are connected with a balanced chemical equation. Okay, part B is how many grams of lead chloride form when 15 grams of aluminum chloride react with 50 grams of lead nitrate. Okay, so yes, also stoichiometry because we're given information about one molecule, asked about another, but part B, you can see that we are given 15 grams of aluminum chloride, a reactant, and 50 grams of lead nitrate, another reactant. So part B is going to be a limiting reactant stoichiometry problem. So we're going to start with an easy, kind of a straightforward grams to gram stoichiometry problem. And then B, we're going to tackle a limiting reagent stoichiometry problem. Okay, so with that said, let's just jump into it because we've got a lot of calculations to do. All right. So starting with A first, this is easy. And this is really, I mean, it is stoichiometry, but it also is very, very similar to just straight up dimensional analysis. So I am going to let my units lead me in a lot of these steps. I'm starting with grams of aluminum chloride. That's my start point, and I'm trying to get to grams of lead chloride. Okay, so start with what we're given. 15 grams of aluminum chloride. Okay, so let's start here. 15 grams of aluminum chloride. All right, whenever we're doing a stoichiometry problem and we're going to have to relate two molecules or two compounds with a balanced chemical equation, we relate them with their mole ratio. This is why we talked about mole ratios last time. So to move in a balanced equation between any two molecules or any two compounds, we have to be first in moles because we use the mole ratio. So that is one point somewhere in the middle that you can know what you're doing is you're going to have to move through moles at some point. Well, when I'm looking at this grams of aluminum chloride, my first thought is I got to do stoichiometry. I can't do stoichiometry with grams. I've got to first convert to moles. So to do that, I'm going to use the molar mass, which I have 133.34 grams of aluminum chloride in 1 mole of aluminum chloride. Okay, you're going to hear me say this. I don't know how many times in this live stream, but I'm going to keep on saying it. Make sure you write your units down and be specific. So I'm not just writing grams here, but grams of aluminum chloride because hopefully at the end of the problem, we're going to end up with grams of lead chloride. So we don't want to just write grams even because we're going to have a couple of grams present. So you want to be specific about the unit. I am converting from grams of aluminum chloride into moles of aluminum chloride. And this is really helpful as we're getting ready to do our mole ratio to know what molecule we're switching in between. And I know the students hate to write down units, and you just want to do the math. But without having the units there, then I guarantee there's going to be a mistake in the math, because I've just seen it so many times. So I know it takes extra time, but trust me, you want to write down your units for this. Okay. All right. So let's keep going with this problem. So now that we have, and actually I'll show this. So my grams of aluminum chloride have canceled. I now have moles of aluminum chloride. Now I'm just going to keep going with my conversion factors. You can stop and actually calculate your moles of aluminum chloride, so you can break this up into multiple steps. If you want, you're going to get the same answer. I like to put this all together and make it one long calculation, basically. So now that I have moles of aluminum chloride, I'm going to convert to the molecule that I'm looking for. And in this case, I'm trying to get to lead chloride. So I'm going to use the mole ratio between aluminum chloride and lead chloride. Okay, so the one I want to cancel is aluminum chloride. So I'm just going to write the unit down. Again, make sure you put what molecule it is. And I'm trying to get to moles of lead chloride. Okay, to get the numbers in front of here, we're going back to the balanced chemical equation. So what number is in front of aluminum chloride? I have a 2, so a 2 goes here. What number is in front of lead chloride? I have a 3, so there is a 3 here. So that is where those numbers come from. I know sometimes students get confused as to, wait, how do you know what number goes in front? And it's all the balanced chemical equation. Okay, so at this point, units, my moles of aluminum chloride have canceled, and I now have moles of lead chloride. So I've used my mole ratio to convert from one molecule, aluminum chloride, to another molecule, lead chloride. But my problem didn't ask me for moles. My problem asked me for grams. So I need grams of lead chloride. Right now I have moles of lead chloride. So I have one more conversion factor, or one more step, you could think about it. And I want to convert from moles of lead chloride to grams of lead chloride. And of course, I do this with the molar mass. So in 1 mole of lead chloride, where is that number? I just had it. Here it is. There are 278.106 grams of lead chloride. So you can see here my moles of lead chloride have canceled. I now have grams of lead chloride, which is exactly what the problem asked me for. So now I'm ready to put it in my calculator. Okay, and I got a question about this recently, about how to put it in your calculator. So when you have it set up like this, anything in the numerator is multiplied and anything in the denominator is divided. So when I put this in my calculator, I take 15 and I divide by 133.34. Then I multiply by 3, and then I divide by 2. And then I multiply by 278.106. So you can see, again, anything in the numerator is multiplied, and if it's in the denominator, you are going to divide. But that is how I put it in my calculator. I know some other people, so here's another way you can put it in your calculator, is they will multiply all of the numerator numbers and then divide by all of these guys multiplied together. Mathematically, it's totally the same. It's what makes the most sense to you. Okay, all right. So let's go ahead and get this number. We have 46.9 grams of lead chloride. Okay, so we have answered our question. That's fantastic. This one is done. So this is what I would call a simple stoichiometry problem. We can do it in one step. We just have to watch our units and use our mole ratio to convert between molecules. But now we have to do a limiting reagent problem. And I think for this one, I'm just going to go ahead and switch to my next page because this is going to take some space. Okay, so let's rewrite our balanced chemical equation. Okay, so this is lead nitrate and aluminum chloride. And just for time's sake, I am not putting in all of the states. Okay, PbCl2. Okay, so what we've got is we have 15 grams of aluminum chloride, which is what we had before, and we have 50 grams of lead nitrate. Okay, just to summarize, again, I'll pop back here, just to summarize what the problem gave us. These are our critical pieces of information. 15 grams of aluminum chloride, 50 grams of lead nitrate, and again, we're trying to get to lead chloride. So I am going to go ahead and just go lead chloride, question mark. Okay, so to do a limiting reagent problem, we need to first figure out which one of our reactants is going to run out first, because that is going to limit how much product we're going to form. So in order to do that, I need to be able to compare the two reactants, which means I need moles. So both of these are in grams, so I'm going to convert both of them into moles for my first step. So let's start with my 15 grams of aluminum chloride. Whoops. Al, I forgot my L there. Of aluminum chloride. And let's just do a simple conversion into grams. Again, same molar mass as before, obviously, because that does not change. And this is 1 mole of aluminum chloride. Okay, so this gives me 0.1125 moles of aluminum chloride. Okay, great. Let's do the same thing for our lead nitrate. We have 50 grams of lead nitrate. And again, just using the molar mass, which is 331.21 grams of lead nitrate over 1 mole of lead nitrate. Okay, and this gives me 0.1510 moles of lead nitrate. Okay, again, this is why I say make sure you're specific with your units, because even if you just put moles, you would have 2 different numbers here that are moles, and it's very hard to keep track of what is what unless you specify that you've got moles of aluminum chloride here and moles of lead nitrate here. Now, the other thing that I wanted to point out is it's very tempting initially to look at this problem and say, well, I've got 15 grams of this reactant and 50 grams of this one, so for sure it's the aluminum chloride that's going to run out first. Well, actually, you don't necessarily know that. So look what happened even as we just converted into moles, because lead nitrate is really, whoa, that is extra massive. Sorry, that should just be 331, not 3,000. Lead nitrate is really massive, so it's actually got a fewer number of moles. And even looking at your moles here, it's tempting to go, oh, well, I just need to pick the smaller number, right? So again, it's still going to be the aluminum chloride. But remember, in your balanced chemical equation, you have a 3:2 ratio, and we need to take this into account. So while I know that picking the limiting reactant does take time and it takes a lot of calculations, you really can't just look at something and especially compare grams and go, oh, well, this one is a smaller number of grams, it's going to run out, because you don't necessarily know. You've got to do the calculation first. So speaking of the calculation, let's make sure there are no questions. There are no questions so far. Let's run our test. So what I'm going to do is I'm going to figure out which one is going to run out first by running a couple of tests. Let me switch this over to green. Okay, so this is my testing phase. So I'm going to start with my moles of aluminum chloride, because why not? We'll actually run the test for both of these. You don't have to, especially if you're in a situation where you're under time pressure, like a test or a quiz. You don't have to run both of these tests. Okay, so the question I'm asking myself is, I have this many moles of aluminum chloride. If I'm going to use all of this up in the reaction, how many moles of my lead nitrate do I need to do that? Okay, so all I'm doing is using the mole ratio to convert from aluminum chloride to lead nitrate. So I want to make sure that my moles of aluminum chloride cancel, so that goes in the denominator. And again, I'm going to my moles of lead nitrate to, okay, so that cancels, and I get 0.1688 moles of lead nitrate. Okay, and here is where we need to think through the calculation we've done and decide which one is the limiting reactant. Again, if I'm going to use all of my moles of aluminum chloride, I need to have at least this many moles of lead nitrate. Again, if you remember our sandwich problem from last time, if you're going to make 3 sandwiches, how many slices of bread do you need? You need to have at least 6. So this is how many moles I'm going to need of my lead nitrate. Okay, so now I'm going to walk over to my pantry. How many moles do I actually have? Do I have enough? And you can see I don't have enough. I need 1.688, but I only have 1.510. So I am going to run out of lead nitrate before I can react all of my aluminum chloride. So what I like to do is I like to say, not enough. And then I come up here to my lead nitrate. I'm going to put a box around it. And I'm going to say limiting. Okay, so I have identified my limiting reactant, but you can also, so if for this test I started with my aluminum chloride, but we can run the same test. With this time let's start with the lead nitrate. If you have the time and you just want to be sure that you've picked the correct limiting reactant, you can run both tests and they should confirm the same limiting reactant. Okay, so let's start with our 0.1510 moles of lead nitrate. Okay, and this time I'm just converting from lead nitrate into aluminum chloride. Again, the question I'm asking is if I'm going to use all of my moles of lead nitrate, how many moles of aluminum chloride do I need? Okay, that cancels. And I need 0.1007 moles of aluminum chloride. Okay, so if all of my lead nitrate reacts, I need to have at least 0.10007 moles of aluminum chloride. How much do I have? So again, I think of this as like walking over to my pantry. I know how much I need, open up the pantry, how much do I actually have? And you can see that I've got extra. I have plenty, no problem. I've got extra aluminum chloride. So again, what I write down here is excess. So that means my aluminum chloride is in excess, which again says that my lead nitrate is my limiting reactant. Again, both tests will lead you to the same limiting reactant, which is why you only need to run one. But again, if you want to confirm, you can run both. Okay, so now that we have identified our limiting reactant, we can actually do our problem. See, I gave myself an extra page, and I should have given myself 2. So let me give myself an extra page here. All right, so any calculations that I do from this point, I am going to use my limiting reactant to do. So I am going to start with my moles of limiting reactant. All right, so here is my moles of lead nitrate. The other thing that I think is good about this problem is, again, when you looked at just the grams of the 2 reactants, you might say, oh, yeah, aluminum chloride is so much smaller, it's totally going to run out. Even if you had looked at moles and you'd pick the smaller one, you would have still picked the wrong one. This is why we run the test to see which one actually runs out first. Okay, so now I am predicting products from this, and I'm trying to get to my lead chloride. So I need my mole ratio between my lead nitrate here and my lead chloride. So let me come back here and write that in. So the nice thing is it's a 1-to-1 ratio, but it's a 3-to-3 ratio, which means I don't have to do a lot of extra math here. And this is moles of lead chloride. I always love it when the ratio is reduced to 1-to-1. Okay, so you can see, whoops, I'm going to switch to my green. My moles of lead nitrate have canceled. Now I have moles of lead chloride, but my problem asked me for grams, so I have one more step. We are almost there. I promise, I promise, I promise. We just need to convert this moles of lead chloride into grams of lead chloride. We're using the molar mass. Okay, so for every 1 mole of lead chloride, there are 278.106 grams of lead chloride. Okay, so let me show how my units cancel. Moles of lead chloride cancel. Now I have grams of lead chloride. So now I'm ready to put in my calculator, and I get 42.0 grams of lead chloride. Whew. Okay. I know these limiting reagent problems are really long. And again, you're going to get tired of writing down all your units, not only the moles and grams, but what molecule it is. But I mean, I promise that this is what you want to do to avoid mistakes. Okay, any questions about this one? No, it looks like we're good. Okay, let's go on to our next problem. Okay, so this one we're going to start using some density. So that our previous problem was just grams to grams, simple stoichiometry limiting reagent. So now I want to mix it up a little bit, and let's talk about what happens when you have density in a problem. Okay, but let's just read it first. So again, we're given a balanced chemical equation. This is a combustion reaction. And we're asked how many grams of water is formed when 30 milliliters of C6H6, this is actually benzene, react completely. And they give us the density of benzene as 875 kilograms per meters cubed. Okay, this is not uncommon. You can see in our chemical reaction, benzene is a liquid, and that's true, benzene is a liquid. So sometimes you might measure this out in terms of a volume instead of measuring out an amount of grams. It depends on what you have on hand and how it's easiest to measure. So if we're ever given a volume here and we need to do stoichiometry, and this is not a concentration problem because we just have pure benzene here, then we need to deal with a density. So a density is going to let us convert between mass and volume. So in this case, we're going to go volume to mass, but you can also go mass to volume, which we'll actually do in the second part. So you need to look at the units of density, and you can see I've got a mass here and a volume here, so we can use it to go in between each. Okay. So, all right. Oh, sorry, Jessica, you had a question. Oh, no, that's fine. All right. Enjoy the rest of your evening. Thanks for popping in. All right, so let's go back to this problem. We have 30 milliliters, and we want to go to grams of water. So this is also a stoichiometry problem because we're given information about one molecule, and we are asked about another molecule, and we connect them with a balanced chemical equation. This means at some point, I'm going to have to go to moles. Well, I've got a little bit farther to go because I've got milliliters. So I've got milliliters. I'm going to use my density to eventually get that to grams. Once I'm in grams, I can use molar mass to convert to moles. Then comes my mole ratio. Then I can predict my product. So that is my very rough path from the start to the finish. And I like to kind of at least roughly plan this out in my mind before I start putting pen to paper. But some people like to just start putting pen to paper and working the problem like that. Again, whichever way your brain works best here. Okay, so let's start with what we're given. We've got 30 milliliters of benzene, so we're going to start with that. So 30 milliliters of benzene. Now I know I'm going to use my density to convert between my volume and grams, and I need to do that because I need to eventually get to moles. But right now I have milliliters as my volume, and this is meters cubed. So those are not the same unit. So there are two different ways that you can approach this. You can take your density and convert this from kilograms to meters cubed to grams per milliliter and just convert the density itself and then use that converted density. Or what I'm going to do is I'm actually going to convert my milliliters into meters cubed. It doesn't matter. You just do it the way that makes the most sense to you. Okay, so I know that in 1 milliliter there is 1 centimeter cubed. Great. Okay, that at least gets me to a cubed unit. Now, how do I go from centimeters cubed to meters cubed? Well, I know that there are 100 centimeters in 1 meter. Okay, so that's one step, but this is centimeters cubed. How do I handle that? You're just going to cube the denominator and cube the numerator, just like that. Okay, so let's show how my units are canceling. So my milliliters of benzene have canceled, and see, look, I have messed this up already. This is still C6H6. All of these are C6H6 because we're going to convert between molecules. So I need to be very specific here. Okay, so my milliliters have canceled. Now my centimeters cubed have canceled, and now I have meters cubed. At this point, I can use my density because I have matched the unit of my density. And I do want my meters cubed to cancel. So my 1 meters cubed of benzene does go in the denominator, and I have 875 kilograms of benzene in the numerator. Okay, so check this out. My meters cubed of benzene has canceled. Now I have kilograms of benzene. So this is now looking more like our first problem where we had grams, except I've got kilograms. So I've got to deal with that first, but at least that's pretty easy. So all I need to do is in 1 kilogram of benzene, I have 1,000 grams of benzene. C6H6. Okay, I am continuing my fence post down here because I need more space. So let's show how we're still canceling. So I'm canceling out my kilograms of benzene. Now I have grams of benzene, which means I can finally use my molar mass and convert to moles. All right, so we're getting there. Oops, let me switch colors. So 78.11 grams of benzene and 1 mole of benzene. Oof. This is a really long one. Okay, so my grams of benzene have now canceled. I've got moles of benzene. Now I can think about actually my stoichiometry. So I'm starting with benzene. I'm trying to get to water. So I need my mole ratio between benzene and water. So I want of course, my moles of benzene should cancel. And I'm trying to predict moles of water. Now I need to know what numbers to put in here. Again, I am just going to go to my balanced chemical equation. So in front of benzene, I have a 2. So I'm going to put a 2 here. And in front of water, there is a 6. So I'm going to put a 6 here. And you can see that now my moles of benzene have canceled. I have converted into moles of water. So at least I am at the right molecule. But of course, the problem is it asks me for grams of water. So I have 1 more conversion factor to put in. And that is the molar mass of water to convert from moles of water to grams of water. 0, 1. Yeah, grams of water. Okay, so my moles of water have canceled. Now I have grams of water, which is what the problem asked me, so I'm finally ready to put this in my calculator. This was a really long one, and this is usually the case when you've got density. Sometimes it'll just add 1 step, and in this case it added like 3 or 4 different steps. It just depends on what units you're starting with and what units your density come in. But you can see all I did was I just made sure that my units were canceling, and I just worked. I think of it as letting your units lead you. I just worked until I got to the units that I wanted, which were grams of water. Okay, so when we do this calculation, we get 18.2 grams of water are formed. Okay, that's fantastic. Let's go on to part B. Okay, so this one says how many milliliters of benzene, or C6H6, is needed to produce 150 grams of CO2. Okay, so this is kind of the opposite. We know we want to produce 150 grams of carbon dioxide, but to predict benzene, that's fine. That's just stoichiometry, but we got to get back to milliliters, which means we're going to use the density again, but we're going to use it on the other end of our calculation. So in part A, we started with trying to get using our density before we did our mole ratio, before we did our stoichiometry. But in part B, we're actually going to do our stoichiometry first and then use our density. And I'll show you what I mean, but of course I need an extra page here, so let me put an extra page. Okay, let's write our balanced chemical equation because we're definitely going to need that. Okay, plus 15 oxygen gives us 12 moles of CO2 plus 6 moles of H2O. Okay. All right, and we are starting with 150 grams of carbon dioxide. At least let me just double check and make sure I got that number right. Yes, we're starting with 150 grams of carbon dioxide. And again, we are trying to get to milliliters of benzene. I'm going to have to do stoichiometry, which means I'm going to need a mole ratio, which means I need moles. So I can't have grams of carbon dioxide. I've got to get to moles of carbon dioxide. So I'm going to use my molar mass to convert from grams of carbon dioxide into moles of carbon dioxide. All right, so here is my molar mass of CO2 and 1 mole of CO2. Okay, great. Let's show how my units are canceling. So now I've converted into moles of CO2. So now I can use my mole ratio to move from carbon dioxide to benzene or C6H6. So I know I want my moles of carbon dioxide to cancel, and I'm trying to get to moles of C6H6 or benzene. So again, I'm going to look at my balanced chemical equation. What is my number in front of carbon dioxide? That is a 12. So I put a 12 here. And again, for my benzene, I've got a 2 in front of the benzene, so a 2 goes here. And then you can see my moles of carbon dioxide have canceled. Now I have moles of benzene. But of course, I'm not finished because I'm looking for milliliters of benzene. So I've got a few steps yet to tack on. So if I'm thinking, all right, how am I going to get from moles to milliliters? Because of course I don't have a conversion that's straight from moles to milliliters. But I think the easiest thing to do is to use the molar mass, go from moles to grams. Then it's easy to go from grams to kilograms. At that point, I can use the density, and then I just have to do a conversion from meters cubed to centimeters cubed to milliliters. I know it's a lot of steps, but it shouldn't be that difficult. Okay, so but benzene, so yes, use the number of, no, so we don't use the number of carbons for benzene. We need to make sure that we're looking at the whole molecule if you're talking about the molar mass. And yes, so if you burn 2 moles of benzene, you're going to get 12 moles of carbon dioxide. So it sounds like maybe you've got a question about how to balance chemical equations. And I want to say we did that maybe 2 or 3 live streams ago. So you might want to check out that live stream on how to balance chemical equations there. Okay, so let's continue on with our problem here. So my next step, I shouldn't say first, my next step here is to convert from moles of benzene into grams of benzene. I do that with my molar mass. So in every mole of benzene, there are 78.11 grams of benzene. I'm going to have to continue this on to the second line, of course, because I just don't have enough space. All right, so let's show how units are canceling. Here go my moles of benzene. And now I've converted into grams of benzene. But to use my density, so maybe I'll write my density up here. So remember the density is 876 kilograms per meter cubed. So it's got kilograms in it right now. I'm in grams. So I'm going to do a quick conversion into kilograms. So for every 1,000 grams of benzene, that is 1 kilogram, again, of benzene. All right, and so what this allows us to do is to cancel out our grams of benzene. Now we've got kilograms of benzene. Again, I converted into kilograms to match my units and my density, because now I can use my density, C6H6, into 1 meters cubed of C6H6 to get into meters cubed. So at this point, what I've done is I've converted from a mass into a volume. Meters cubed is a volume. You can picture a cube that is 1 meter by 1 meter by 1 meter, and that is a meter cubed. It's a volume, it's a box. But my problem asked me for milliliters, so I can't just stay in meters cubed. I need to convert to milliliters. Now, unfortunately, there's not just one simple way to convert from meters cubed into milliliters. I mean, you can look up that conversion factor. I'm sure Google knows it. But I'm actually going to use centimeters cubed to convert that. So I know in 1 meter, there are 100 centimeters. All right, but meter does not cancel with meters cubed. That would give me meters squared. So what I'm going to do is I'm going to cube the denominator. I'm going to cube the numerator. Then my meters cubed cancels. And of course, this is all benzene here. This is C6H6. Putting in the molecule also is going to make sure if you have a problem with 2 or more densities, you're going to want to be really careful that you apply the correct density to the correct molecule. Now on this one we only have 1, but we could have had more than 1. And then I've just got one more, just very easy conversion factor. And 1 centimeter cubed, there is 1 milliliter. Okay, so at least our very last conversion factor is just 1 to 1, and that makes it easy. So if you look at, again, all of the units, you can see everything has canceled until I get to 1 milliliter. And of course, that is 1 milliliter of benzene, C6H6. All right, so this is a really long calculation. One thing I will point out, you've got this 100 cubed in the numerator, so just make sure you don't forget about cubing that 100 when you do this calculation. All right, so my final answer is 4.437 times 10 to the 4th milliliters of benzene. So take a big deep breath there. You have made it. So that one is a not only just more difficult because of the density, but because the density is in kilograms per meters cubed. Again, which is why some people like to say, I don't want to use those units for density, so I'm going to actually take the density and convert it into grams per milliliter, which is totally fine. You can do that as well, and you'll get the same answer. Okay, let's go on. We've got one more problem to do, and I think we can make it. At least we can make it through part A. Okay, so again, balanced chemical equation. You can see I have, well, that's a solid. I have gases and a solid here. All right, so how many atmospheres of ammonia and carbon dioxide are needed to produce 2.5 kilograms? And this is actually urea, CH4N2O. We know the volume of the reaction vessel is 50 liters, and the temperature of the reaction is 75 degrees C. Okay, so this is still a stoichiometry problem. We are given information about, several molecules here, and we are asked about other ones. So we know we've got 2.5 kilograms of urea, and we want to know pressures here. So we're going to have to convert from urea into both ammonia and CO2. So it's really asked us 2 questions in one here. Okay, so if I'm going to do stoichiometry, of course, I've got to get to moles, but there's a twist here with this one, right? So it didn't ask me grams or moles, it asked me atmosphere. So that is a pressure. That means we're dealing with gases, which of course, yes, we're dealing with gases. These both specify that they are gases here. So when we're dealing with gases, we're going to use the ideal gas law. And let me just write it up top. So if you remember, ideal gas law is PV equals nRT. All right, P is pressure, which can be measured in atmospheres. That's one way you can measure pressure. V is volume. N is your number of moles. R is your universal constant. And T is your temperature in Kelvin. So this is why we are also given the volume, and we're also given the temperature of the reaction, because we've got to get to a pressure, which means we need to be able to fill in here. Okay. But we were given 2.5 kilograms of urea. So my first thought is I can go ahead and at least convert this kilograms of urea into moles. And once I'm in moles, then I can kind of do both calculations, and I can do both sets of stoichiometry, because we're going to have to do one stoichiometry calculation from urea to ammonia, and then another one from urea to carbon dioxide, because we've got different mole ratios for each of those reactions. So this is not just one calculation, this is multiple calculations. So let's start with our 2.5 kilograms of urea, and let's just get that to moles, because that's going to take 2 steps, because of course we're starting with kilograms here. Okay, so we have kilograms of urea. So my first step is to convert from kilograms to grams, because to get to moles, I have to use the molar mass. And the molar mass, of course, is just grams per mole, not kilograms per mole. Okay, CH4N2O. Then I'm going to use my molar mass, grams of CH4N2O, and 1 mole of CH4N2O. All right, so let me show you how units have canceled here. So my kilograms of urea have canceled. My grams of urea have canceled. And this gives me 41.63 moles of urea. So CH4N2O. Okay, great. Now I've got moles. Now I'm ready to go ahead and do my stoichiometry. So I'm going to do my stoichiometry first on my ammonia just because it happened to be written first. So taking my moles of urea, sorry, not grams. We just did all that work to convert to moles. Okay, moles of urea, N2O. Let's use our mole ratio. And let's go to moles of ammonia. So I know I want my moles of CH4N2O to cancel, and I'm trying to get to moles of ammonia, NH3. So again, I go to my balanced chemical equation. There is no number written in front of my urea, which means we assume it is 1. And in front of my ammonia, there is a 2. Okay, so I'm just multiplying by 2 here. This is pretty simple. 83.25, okay, moles of ammonia. Great. Okay, I'm going to do the same thing and predict my moles of carbon dioxide. So still starting with my moles of urea, because remember, this is a different mole ratio. CH4N2O. All right, so again, I know I want my moles of urea to cancel. I'm trying to get to moles this time of CO2. All right, so let's get our numbers. Again, there's just a 1 in front of the urea. And again, in front of the CO2, there's nothing written, which we assume is a 1. All right, this is a great calculation to do because the number of moles just stays the same. Again, I love those 1-to-1 ratios. So now I have predicted how many moles of ammonia I'm going to get and how many moles of carbon dioxide I'm going to get. All right, this is all great. I have done my stoichiometry. But of course, what is my problem? Ask me for pressure. I need to go to ideal gas law, and I also need to go to a new page. All right, so again, let's start with our ammonia. I'm using ideal gas law here. All right, so let's think about what we know and what we're trying to find. My problem asked me for atmospheres. It's a way to measure pressure. So I'm trying to solve for pressure. That means I need to know my volume, my number of moles, I always know R, and my temperature. So do I know volume, number of moles of ammonia, and the temperature of the ammonia? So yes, hey, look, I've got my moles of ammonia right there. That's easy. Do I know my volume? Yes, the volume of the reaction vessel is 50 liters. Do I know my temperature? Yes. So the reaction is at 75, which means everything's at 75 degrees C. So I have all the information I need to solve for my pressure. Okay, so my pressure, I don't know, so I'm just going to leave that P. My volume is 50, that looks a little bit like a 3, 50 liters. I just calculated my number of moles, that is 83.25. This is moles, again, NH3. Now we're going to have to apply ideal gas law twice, so it is important that you don't just put moles here, but you keep track of which compound or which molecule you're talking about. Now, my value of R, this is dependent on what my units for pressure and volume are. So I want pressure to be in atmospheres, and of course my volume is given in liters. So my value for R that I'm going to use is really the most common one, I would say, because this gives me liters, atmospheres over mole K. So that means my volume has to be in liters, which it is, and my pressure is going to come out in atmospheres, which is what I want because that's what the problem asked me for. Okay, but notice this one other thing. My temperature must be in Kelvin. I have it in Celsius. So let me put this in green because I'm going to need this again. So I have 75 degrees Celsius. How do I convert this to Kelvin? You add 273.15. Whoops. That was weird. Okay, 273.15. I don't know what happened to my stylus there. Okay, so my temperature is 348.15 K. So when you use ideal gas law, you are always, always, always going to convert to Kelvin. Why do we convert away from Celsius and into Kelvin? Because we need to get to the absolute measure of the temperature. And of course, degrees Celsius is a relative measure. It's the same as degrees Fahrenheit. Those are both relative ways to measure temperature, and we need an absolute way. So we're always going to convert to Kelvin. This is a very common mistake that I see in a lot of students' papers is they've got their method correct, but then they forget to convert their Celsius to Kelvin. And this is obviously going to make a very different answer if you don't convert to Kelvin. All right, so Kelvin. So what I want to show you here, and which is why we always write down our units. I know I just keep saying it over and over. Look, okay, my liters cancel, my moles cancel, and my Kelvin cancels. The only thing that doesn't cancel is the atmospheres, which is exactly what I want for pressure. Okay, so solving for pressure, I'm going to get a pressure of 47.6 atmospheres of ammonia. Okay, which is exactly what the problem asked me for. They wanted atmospheres of ammonia. I'm going to do the same thing for the carbon dioxide, except I'm going to have different numbers. So this one's for ammonia. This is for carbon dioxide. And so I like to keep these separate at this point. So again, I can keep track of what's going on with what. Now this is nice because we just have one reaction vessel and we have one temperature. But in the next problem you're going to see we're going to have different ones. You got to keep track of what's going on with what. So again, PV equals nRT. We're solving for pressure, so I'm going to keep that P. We still have a 50-liter reaction vessel. Now, my number of moles is different. So my number of moles of carbon dioxide, you can see here, is 41.63. 41.63 moles of carbon dioxide. Again, this is why it's important that you don't just write moles down, but moles of carbon dioxide. Otherwise, it's very common to flip-flop these two numbers of moles, and then you're getting the wrong answer. Still using the same value for R because it has the units that I want, just like it did for ammonia. Mole K, and of course my temperature is still 348.15 because it said the whole reaction was at that temperature. Okay, so just solve for pressure and I get 23.8 atmospheres of carbon dioxide. Again, let me just show that my units are still canceling like I want them to cancel. And I'm left with atmospheres, which is why I get atmospheres here. Okay, questions about that? Nope, it looks like we're good. I'm going to need another page because we have another problem to answer. Oh, good, we've got 10 minutes. Okay, we can do this. We can do this. All right, so let's go back to our problem and let's read it. So part B, how many grams of urea? Again, urea is this guy right here, CH4N2O. How many grams of urea are formed when 800 milliliters of ammonia at 700 torr and 25 degrees Celsius reacts with 500 milliliters of carbon dioxide at 1.5 atmosphere and 20 degrees Celsius? Okay, so we have a lot of information here. But again, I'm going to walk it back. This is a stoichiometry problem. I'm asked for grams of urea. I'm given information about ammonia and carbon dioxide. I need to link these with a balanced chemical equation. This is not just stoichiometry, but this is limiting reagent stoichiometry because I have information about ammonia and carbon dioxide. These are both of my reactants. So I've got to figure out which one is limiting before I can figure out how much urea is formed. Now, this is not just, like we did in the first problem, grams limiting reactant. I've got volume, I've got pressure, I've got temperature. I'm going to use ideal gas law to get to moles. Okay, so I'm going to do that for both ammonia and carbon dioxide, but this is again a problem where I've got different, you can see I've got different volumes, I've got different pressures, and I've got different temperatures. So I need to be really careful that I keep the information for each molecule with its appropriate molecule, because it's easy to get things kind of mixed up and flip-flopped here. Okay. Whew. We've got some work to do, but we can do it. It's fine. It's fine. It's fine. We're going to do this. It's just going to be fine. It's just going to take us a little bit of time. So let's start with our ammonia. And this is kind of how I keep things together, is I make sure is that I do these kind of headings. All right, so I'm using ideal gas law, which means if I'm going to solve for N, my number of moles, I need to know pressure, volume, and temperature. Again, I'm going to choose my R based on my units. So pressure, yes, I have my pressure again. If I go back here, you can see my pressure is 700 torr. All right, so that's 700 torr. Great. And again, this is all ammonia. This is all ammonia. I want to make sure I don't mix up any of my carbon dioxide in here. Okay, I have my volume. Again, go back. I have 800 milliliters. So this is, I think that was 0.0 milliliters. Great. I'm going to solve for N, my number of moles. All right, so let's choose my R here. So I've got torr and I have milliliter. Of course, N is going to be in moles and temperature has to be in Kelvin. So do I have an R that has torr in milliliters? Well, the problem is I don't. But I do have an R. I'll show you, 62.364. That is liter torr per mole K. All right, this is a pretty easy fix, because all I need to do is change this 800 milliliters into liters. So that's just a quick divide by 1,000. So let's just convert this. 800, there we go, liters. Okay, so now my units match. My pressure is in torr, which matches my R, and my volume is in liter, which also matches my R. Now, the other thing that I need to do is I need to convert my temperature to Kelvin. So my ammonia was at 25 degrees C. Again, I'm going to add 273.15, and this is going to give me my temperature in Kelvin, which is 298.15 Kelvin. Again, this 25 degrees Celsius I got right here. So I'm getting it from the problem, and I'm getting it, whoops, from ammonia. I went too far. My bad, my bad. Okay, so this is 298. I wrote 80. Hello, dyslexia, my old friend. 298.15 Kelvin. Okay, so check this out. Just make sure your units are doing what they need to do. Torr, yes. Liters, yes. Kelvin, yes. I'm left with moles, and N is in moles. So my units are doing what I need them to do. So solving for N, I get 0.03012. These are moles, again, of ammonia, because I'm working with all of the information on ammonia here. Okay. All right, let's go carbon dioxide. Same thing. I'm using ideal gas law. Now I need to be careful that I am using all the information for carbon dioxide and I'm not mixing in any information for ammonia. So in this case, my pressure is 1.5 atmospheres. So check that out. I've got a completely different unit for pressure. This one was 500 milliliters. I'm still going to do N, so I need an R. I need an R that's appropriate for atmospheres and milliliters. Well, I don't have an R that's atmospheres and milliliters, but I do have my R for atmospheres and liters. 206 again, or sorry, liter atmosphere over mole K. So I'm going to do the same thing that I did for the ammonia. I'm just going to do a quick conversion from this milliliters into liters. Again, just divide by 1,000. And that is liters. And my temperature, I got to be careful because I don't want to use my temperature for my ammonia because I have my own temperature here for carbon dioxide. That's 20. All right, so it's at 20 degrees Celsius, still adding the 273.15. And I am getting 293.15 K. All right, so that goes in my temperature. Again, it's really easy to forget to convert into Kelvin. So let's check and make sure my units are okay. So liters are canceling, atmospheres are canceling, Kelvin is canceling. I'm left with moles, which is exactly what I want because I'm going to solve for N. All right, so number of moles for CO2 is 0.03118 moles of carbon dioxide. Okay, so I have taken all of that information from the problem and I have used it to solve for moles for both of my reactants, which means now it's time to do our limiting reagent problem, and I need another page. Okay, so let me just condense this here. I have 0.03012 moles of ammonia, and I have 0.03118 moles of carbon dioxide. So now, just like we did in the first problem, we are going to run our test to figure out which one of these is going to run out first. And we switch to green. All right, so here is our test. I will go through the calculation again for both tests, but if you're in a timed situation, you only have to do one. So testing. Let's test with our ammonia first. So moles of ammonia. The question I'm asking is, if I use all of my ammonia, how much carbon dioxide do I need? All right, so going back to our balanced chemical equation, almost. Ammonia to carbon dioxide is a 2-to-1 ratio. All right, so 2 moles of ammonia to 1 mole of carbon dioxide. So I get 0.01506 moles of carbon dioxide. So if I'm going to use all of my moles of carbon dioxide, I need to have at least 0.015 moles of carbon dioxide. Okay, how much do I have? Again, I'm walking over to my pantry. How much do I actually have in the pantry? Oh, I've got tons. I've got plenty of carbon dioxide. So again, I write this is in excess. So if carbon dioxide is in excess, then my ammonia is my limiting reactant. Okay, so I'm going to write LR here for limiting reactant. But let's run the test for starting with the carbon dioxide, because again, it'll give us the same answer, and it'll just help confirm that we have chosen the correct limiting reactant. Okay, so if I'm going to use up all of my carbon dioxide, how much ammonia do I need? So this time I want my moles of carbon dioxide to cancel. I'm going to moles of ammonia. The ratio is the same, but this time I'm multiplying by 2 instead of dividing by 2. And I get 0.06236 moles of ammonia. This is how much is needed. All right, so I need 0.06 moles of ammonia. I know I've got like half as much as I need. I do not have enough. This is going to be limiting. So again, both calculations give me the same answer. My ammonia is my limiting reagent. We are finally ready to actually calculate our final answer. So starting with the moles of limiting reactant. Again, this is why I like to box it. I like to say specifically that it's limiting, because look at all these calculations you've got going on here. You've got a lot of calculations. You want to make sure that you're using the correct moles, that you're using the moles of ammonia. Okay, so now I am going from moles of ammonia to moles of urea, CH4N2O. Let's go back to our balanced chemical equation. Ammonia's got a 2 in front of it, urea's got a 1. So that is a 2-to-1 ratio. All right, but of course it asked me for grams of urea. So let me just convert that to grams with the molar mass. We haven't used a molar mass yet. The nice thing about ideal gas law is it does give you your amount in moles. So it can save you a little bit there. All right, so let me show. Moles of ammonia have canceled. Moles of urea have canceled. Now I have grams of urea. I'm getting my final answer here. So I will make 0.905 grams of urea. I know that took a lot of pages, didn't it? So I hope this helped with your stoichiometry. Again, these are difficult stoichiometry problems, especially when you're dealing with an ideal gas law. It just brings a lot more calculations in. And again, you have to be so careful that you keep your information with each molecule together with itself and you're not mixing anything up. That's just super frustrating to work through all these calculations, and they're wrong because you've used the pressure for carbon dioxide instead of the pressure for ammonia. Let me know what you would like to see. Of course, we're here for you, whatever questions you have. I'm happy to do some more stoichiometry problems next week, or I'm happy to go to a completely different topic. But thanks so much for joining us, and I'll see you next week. Bye.